Hello and welcome to our introduction to infrared spectroscopy. IR spectroscopy is the measurement of the interaction of infrared radiation with matter by absorption, emission, or reflection. In an era where precise analysis of materials is critical, IR spectroscopy stands out as a cornerstone technique. But how does it work in the first place? Infrared or IR spectroscopy studies the interaction between matter and infrared light. Infrared light is a type of electromagnetic radiation that is characterized by a longer wavelength than visible light. Depending on the specific wavelength range, it can be further divided into near-infrared, mid-infrared, and far-infrared radiation. The interaction between this type of radiation and organic or inorganic matter can be used to perform all kinds of material analysis. Now, let's have a look at how this works exactly. Infrared spectroscopy is based on the principle that matter absorbs specific energy levels corresponding to different vibrational frequencies, also called modes, producing distinct spectral signatures. There are two primary types of vibrations for a covalent bond: stretching vibrations, where the bond oscillates back and forth, and bending vibrations, where the bond flexes up and down. To induce either of these vibrations, the electrons in the bond must absorb a certain amount of energy. The energy required for most bonds in molecules to vibrate corresponds to the wavelengths found in the infrared region of the electromagnetic spectrum. Different types of chemical bonds require different amounts of energy to vibrate. Consequently, each type of bond can absorb specific wavelengths of infrared radiation. In our thought experiment, IR light of known composition is passing the sample and interacts with it. The transmitted portion of light is then collected by a detector. Any wavelengths that are now missing or only show up with very low intensity have likely been absorbed by the bonds within the sample. This absorption pattern, or spectrum, is unique to the material investigated and thus helps us to identify the sample with very high confidence. Basically, that's all you need to know to grasp the concept of infrared spectroscopy. But if you want to know the specifics, for example how spectrum is generated, you must look at the spectrometer. Although today FTIR technology dominates the market, it is imperative to start by explaining the works of a dispersive IR spectrometer. It uses a radiation source, monochromator containing a grating, a sample interface, and a detector. An IR or thermal source are typically inert electrically heated solids that reach between 1000 to 1800 degrees Celsius, promoting thermal emission of infrared radiation. This IR light is directed into a diffraction grating, which disperses the incoming light by wavelength. By mechanically turning this grating, the instrument allows us to select and transmit only the desired wavelength. The resulting monochromatic beam of IR light is directed onto the sample. By repeatedly changing the grating angle, different wavelengths are extracted one by one, and we can scan the whole IR range. The absorption of the sample at each wavelength is then recorded by a detector that turns the transmitted light into an electrical signal, which the software translates into an IR spectrum. While traditional IR spectrometers are able to isolate specific wavelengths for analysis, they are inefficient and slow due to the need to scan each wavelength individually. This is where FTIR spectrometers shine. By utilizing an interferometer, they capture all wavelengths simultaneously, along with a better signal-to-noise ratios and superior wave number accuracy. Let's try to understand this exciting technology by keeping it simple at first. This is a so-called Michelson interferometer. Here, the IR beam enters the interferometer and is directed at a beam splitter, which splits the beam into two separate beams. One of these beams is directed at a fixed mirror, the other at a movable mirror. When the light travels back and is recombined, this causes interference. This recombined beam is then directed at the sample, passes it, and is detected. The interference is the secret behind acquiring all IR information simultaneously. Now, to understand this better, we have to have a look at how light behaves. Light travels in waves with peaks and troughs. Where these peaks and troughs occur in space is called the phase of the wave. Two waves may have different phases, which is called the phase difference. This difference dictates how they interact, which is called interference. If the peaks and troughs of the two interacting waves match up, the waves are said to be in phase, and the resulting interference is called constructive interference. If the peaks of one wave match up with the troughs of the other waves, the waves are out of phase and the result is destructive interference instead. Waves that are not completely in phase or out of phase can also interact in a way that depends on the phase difference between the two waves. The specific way the waves interfere is called an interference pattern. Let us now observe this process as it happens inside the interferometer. Note that the movable mirror is not moving right now. An IR light wave enters and is split in two by the beam splitter. Both waves are reflected by the mirrors and recombined. As both waves travel the same distance, they recombine in phase, producing constructive interference. But watch what happens when we start moving the mirror. The path length for one wave changes, creating phase difference. Now, destructive interference occurs and an interference pattern emerges. This can be recorded as a so-called interferogram that tells us the intensity of all IR radiation based on the mirror position. If we would introduce a sample into that beam, the interferogram would immediately change according to the sample's unique absorption pattern. And since we use all IR light and exactly know the mirror position, we could exactly tell which IR wavelengths were absorbed in one single swoop. However, looking for changes in an interferogram would be quite tedious. This is where Fourier transform comes into play. This mathematical function extracts the individual IR wavelengths from the interferogram, transforming the complex interference data into a clear IR spectrum. In practice, this is done for two interferograms, one with a sample inside the beam and one without sample. The latter provides the so-called background or reference measurement that helps eliminate environmental effects like carbon dioxide or water vapor. The result already looks like a classical FTIR spectrum. As a final step, the sample spectrum is divided by the background spectrum. What we have now is a high-quality spectrum with excellent signal-to-noise ratio, far surpassing dispersive IR spectroscopy in speed and clarity. Despite the sophisticated technology inside an FTIR spectrometer, the technique itself is basically a push-button method, making it an easy-to-use choice for many chemical analysis applications. Imagine an FTIR spectrum like a chemical fingerprint. It can be used to detect dangerous chemicals, characterize exciting new materials, identify unknown product defects, or verify known raw materials. Overall, it is specifically useful whenever quick, clean, and reliable chemical analysis is needed, even for microscopic samples. If you want to know more about IR microscopy, check out this next video. Thanks for watching.